Alrighty, Math All-Stars. It's our time now in order to talk about section 6.1.3. And so the last couple of days we've looked at the law of sines and law of cosines. What we're going to do today instead is we are going to look at what we call the ambiguous case of the law of sines. So I'm going to be going through some stuff. I'll pause the video temporarily to allow you to be able to catch up and do your work. But I would encourage you to follow along as what I am doing here as we move forward. So it says you've been working on solving triangles. But what happens when the given information can possibly form more than one unique triangle? Today you're going to look at solving triangles when information given includes two sides and the angle not between them and is iterated at the top. This is referred to as side-side angle. Okay, so when we have a side-side angle relationship. So our work is going to start on problem number 40. It says that Sharika, Ivan, and Maria are having a snowball fight. Okay, Maria and Sharika have teamed up against Ivan. Maria is 24 feet to the right of Sharika and 18 feet from Ivan, who is hiding behind a tree. Okay, hi, Ivan. So from where Sharika is standing, the angle between Ivan and Maria is 43 degrees. So let's take a moment and let's sketch the situation that we have here at hand. So here's a possible picture. The wording is kind of weird, but from Sharika, the angle to Ivan and to Maria from that point is 43 degrees, as indicated right here. And then this distance is 24, and here is 18. So that's a possible picture that we can draw. Sharika apparently also knows that Ivan can't throw it farther than 20 feet. So apparently Ivan needs to get in the weight room a little bit, or Sharika just knows some really random facts about Ivan. And so we want to know, is she safe? Or in essence, can we figure out this distance right along here from S to I? Okay, and so if that distance is less than 20, she's not safe. If it's more, then we might have a little bit of a situation. All right, so now what I'm going to do is I want to try and call this, well, I'll call this side length little m. And so this is little m right here. And I can use the law of sines in order to solve that. So what I'm going to try and do now is I'm going to use the law of sines. And I'm first going to try and solve for this angle I up here. All right, and so once I get angle I, then I have an angle pair relationship between I and 24, at which point then it's going to allow me to find this angle here, M, and I can then use M and little m down here in order to try and find out that missing side leg. So in essence, what I'm doing is I'm using the law of sines twice, or solve this triangle. And so I'm going to pause the video here for a moment. You should use the law of sines 2 times. First of all, set it up to try and find this missing angle I. And you can use the angle pair relationship of I and 24 with 43 and 18. Once you find I, then you can solve this angle, this angle M pretty easily. And then use that information to set up the law of sines one more time to be able to find the distance of little m. So I'll pause the video. You go ahead and try and solve for the triangle and determine, is she safe? Is that length m less than 20 feet? All right, so what I did is I first calculated angle I up here, and I got I to be 65.413 degrees. After that, I was able to use the triangle sum theorem, and I got angle M, this angle right over here, to be 71 and change. So then I could set up the law of sines, sine of 43 degrees and 18. I used that ratio and then set up this ratio here, angle pair. And I got that M was equal to 25.081. So yeah, she is safe because she is more than 20 feet away from Ivan. So Ivan's got to get in the weight room a little bit, but this is just a good reminder for the law of sines, and what it's going to do is it's going to lend itself useful to what we're going to do here momentarily in figuring out another possible outcome. So now I'm on to problem number 41, and all of a sudden it says, uh-oh, Sharika's getting peppered by Ivan. Either he got in the weight room or he must be less than 20 feet away from her. How far away is Ivan from Sharika? And so all of a sudden we have this situation now where Ivan is just peppering Sharika, but I thought we calculated on the previous problem that we had, that she was more than 25 feet away. So how is this happening? and thus enters today what we're talking about in terms of what is referred to as the ambiguous case of the law of sines. And so what happens in the ambiguous case of the law of sines is the fact that there's actually two different triangles that can be formed when we are given a certain set of criteria, and that criteria is SSA. And so this can produce two different triangles. Okay, so this produces two different triangles, and so we have to solve for the measurements within both of the triangles. All right. Now, in order to construct these two different triangles, what I'm going to do is I'm going to draw a triangle, and I'm always going to label my triangle this way. Okay, I'm always going to put, ooh, that was a crappy side length. I'm always going to put my fixed angle down here. So I'm going to put the 43-degree angle down here. Okay, so that can't change. That's where my angle is always located. And then I'm always going to put the measurement that I know, one of them, on this length up here. So I'm going to call this distance 24 feet. So that would mean that this point down here at the bottom, this vertex, is vertex S. All right? And what we calculated in the last problem is that this triangle would continue to be formed this way. Okay, so up here would be M. All right, and down here would be I. And the other measurement that we were able to find is that this was 18 feet right here. However, what is not fixed in this side-side angle relationship is this distance right here. And what I mean by not fixed is the fact that I can draw another triangle from this given set of criteria, this side-side angle criteria where the angle is not in between the two side lengths. I can create another triangle by doing the following, and watch carefully what I do here. I can take that length of 18 feet, and I could pivot that side over here to create another smaller triangle where this distance along this side is still 18 feet. It's just now that it's swung over to this side. And so now I have this measurement right here also as 18 feet. Okay, so hold our horses. What do we got going on right now? So we have two different triangles that have been formed. And so what I want to show you, first of all, is that we have this first triangle that we found the measurements for in the last situation. Okay, that triangle outlined in blue. And what we found, the distance from S to I, okay, that distance from S to I, we calculated to be more than 20 feet. In fact, it wasn't 20 feet, but rather we found out that that was 25.0081. And so that was the distance from here to here. However, there's actually, as we can see now, another triangle that can be formed, and we were not able to calculate this measurement on the bottom. Okay, I'm going to call this point right here I prime, as indicated with that little apostrophe. And so now I have a second triangle. Okay, I have another triangle that's going on. And so now pay attention with what I'm doing here. This is where I start to lose people from time to time. What I want you to recognize is that this side length right here of 18 feet is the same angle as this one, or not the same angle, but rather the same side. So this triangle right here is an isosceles triangle. Okay, and why that is important is because that means that both of these base angles are going to be the exact same. This angle and this angle are the exact same. Okay, the base angles are the same. Fortunately for us, we know that the measure of angle I from the previous problem, we calculated that the measure of angle I was equal to 65.413 degrees. Okay, 65.413 degrees. So that means that that's the exact same measurement as this angle right here. All right, so what I'm going to do is I'm going to recreate this smaller green triangle so I don't continue to overlap everything that's going on. This is I prime down here. I have M, I have S, and then my other measurements I have are 24 feet, 43 degrees down here, and I know that this is 18 feet. Okay, what I just calculated, or what I just put on, was the angle on the right side. Okay, this angle right over here to be 65.413 degrees, and that's going to be important for us, okay? I know that that's 65.413 degrees, and the reason that's important is because I can find the other angle just on the inside, or this angle right here, by taking 180 degrees and subtracting that from 65, or subtracting 65.413 from 180, because those would form a straight line as such. Okay, so I can do 180 minus 65.413 degrees. So if my public school math is correct, I think that that angle down there, angle I in the green triangle, is going to turn out to be 114.587 degrees. Okay, 114.587 degrees. And why do I need that, or why is that necessary? Well, because now what I can do is I can determine this missing angle right up here, the measure of angle M. And if I can find the measure of angle M, I can then use that to solve for this missing side length across from it, which is what I want to try and find. Okay, that missing side length from S to I represents this distance from Sharika to this new supposed distance where Ivan is standing. So I can calculate the measure of angle M up here. I know that the measure of angle M is going to be equal to 180 degrees, subtracting 65.413, subtracting 114.587. And as such, what that yields for me is 22.413 degrees. Okay, stick with me now. Stick with me. Now I have the opportunity to use law of sines to find this missing measurement, little m, down here at the bottom. Okay, I can set up the law of sines, and so I can say that I have the sine of 22.413 degrees over m, and I can set that equal to the sine of 43 degrees over 18. Okay, that's the ratio that I can set up. All of that work was to set up the law of sines to solve for that missing side length from S to I. So as I go to solve for m, I'd cross multiply, and then I would end up dividing, and I'd get that m is equal to 18 times the sine of 22.413, all divided by the sine of 43 degrees. And now when I type that into my calculator, I get that that distance m is 10.063. And so that means that Ivan was 10 feet away, roughly, from Sharika. And so we have this mysterious second triangle that is created, and the next problem is going to highlight how we can recognize that moving forward. So on problem 42, it says, in the snowball situation, why are there two possible triangles? Well, I'm going to respond to that in two different forms. First of all, side-side angle is not a congruence condition. Okay, thinking back to how you can show that two triangles are congruent to one another. We have side, side, side. We have side, angle, side. We had angle, angle, side, and we also had angle, side, angle. However, this combination of side, side, angle is not a congruence condition. So anytime that you have a triangle with the given markings of an angle and then two sides that are not in between that angle, marked with another triangle, there are more than one triangle that can be formed with that given situation, as found by swinging this other side length over here, because that angle in the middle right here is not fixed, and so you can swing that side length back and forth. Now, to be more technical, why is there two solutions? Why were we able to get like 10 feet and 25 feet? Well, a lot of this can go back to the unit circle. If I were to draw a unit circle here, remember, here's x, here's y. Remember in the first problem, we got 65 degrees roughly for one of those measurements, angle I. We got that the measure of angle I was 65 degrees. So 65.413 to be honest with you, or to be more precise. 65 degrees, if I were to rotate 65 degrees, would put me somewhere right here in the first quadrant. All right? And so that's where 65 degrees is. And so if I were to draw in an angle that would form that, I could get this measurement right here. And remember that sine is dealing with the y coordinate. And so when I look at the y coordinate, I know that there's actually going to be another y coordinate that has that same value over here in the second quadrant. And so the angle that I could draw in up to that point would also have the same y quadrant, or y coordinate rather. And it so turns out to be that this angle right here, the angle that is formed to be able to get to that point, is the angle that we used in the second problem, where we calculated that value of being roughly 120 and change. Why can't I remember that off the top of my head? Forgive me. Rather, 114.587. Okay, so when we're using the law of sines and you have a side-side angle relationship, it is possible that because that side length is not fixed, that we can get two different triangles because we have two different possible y values within the first or second quadrant. And so I know that's a little deep, but for right now, big idea is if you're given a side-side angle relationship, be leery of that there are two possible triangles that can be formed. All right, so what we're going to do now is we're going to move ahead to problem number 44. It says for each triangle below, determine how many possible triangles can be formed with the given information. Okay, so we're going to figure out how many different triangles can be formed. And so in both situations, hopefully you can recognize here that this is a side-side angle relationship. So it is possible that we could get more than one triangle. All right, it's not every case where we have side-side angle that we could get more than one. But what we want to do first of all is I want to reorient these triangles. Okay, I'm going to look at letter A here to begin with, and I always I always like putting my triangle with the two fixed sides in this particular orientation, where the side length or where my angle 38 still stays down here, but 6 now is going to go up on this edge and 24 is going to go here. So in essence, what I did is I put that 6 up being that diagonal length. And so what I can do then is I can take this other length of 24 and swing that over in this particular direction. Because recall that both of these lengths here and here are going to be the same. And so that's going to be a distance of 24 feet here as well. And so within my picture, this up here would be E. This is going to be F. This point right here is going to be D, and I'll call this D prime. All right. And so the distance then from E to D, or excuse me, from E to F is 6. From F to D is 24. And what we want to try and figure out is it possible to have two different triangles? Like, can this actually be a reality with the given information? So in order to do that, what I want to try and locate first is the measure of this angle right down here, the measure of angle D. And what I'm going to do in order to obtain that is I'm going to use the law of sines. So I'm going to find the measure of angle D to begin with. And so in order to determine that, I'm going to say that the sine of D over 6, notice this angle pair relationship here, is going to be equal to the sine of 38 degrees over 24. Okay, so it doesn't matter, but what I'm doing right here is I'm doing sine of 38 over this 24, allowing me to find this missing angle D in my quest to try and determine if there are two or more triangles possible. So you'll see here in a moment what I'm doing. So as I go to try and solve, what you can notice is that when I solve for D, I'm going to get the sine of angle D after cross multiplying and dividing. It's going to be equal to 6 times the sine of 38 degrees divided by 24. So now don't remember when you're finding a measurement of an angle, you're going to take the inverse sine of both sides. So the inverse sine of 6 times the sine of 38 degrees over 24 then is going to yield for us that D is going to be equal to 8.854 degrees. Okay, so that's actually a very small angle measurement. Okay, very small. 8.854 degrees. Awesome. Great. So what I'm looking at now is I'm going to be looking at this triangle. Okay. Oop. By that triangle, I mean the following. The large triangle right here. Maybe I'll just draw that out over here. EFD. I know that the measure of angle E is 38 degrees. I just found that this angle measurement down here is 8.854 degrees. So that tells me that if I took 180 minus those other angles, I would end up getting 133.646 degrees. Okay, so in the big triangle, I have that measurement right there. Okay, now what we're going to do is we're going to go down and we're going to isolate the smaller triangle. Okay, so this smaller triangle that's here with E, F, and D prime. And I'm going to recreate that as such. E, F, D prime. Okay, now stick with me. I know that this angle right here, okay, this angle formed here on the inside, 38 degrees. No, excuse me, not 38 degrees. But this angle right here is going to be the same as this one over here, because recall that this is an isosceles triangle. So these two angles are going to be the same, which tells me that this angle is going to be 8.854 degrees. Okay, why is that important? That's important because I can now calculate this measurement here. That measurement is going to be 180 degrees minus 8.854 degrees. And so that yields 171.146. Okay, 171.146 degrees, which then allows me to be able to determine what the measure of angle F is. Because recall, angle E is still 38. That hasn't gone anywhere. But maybe now you have some red lights flashing within your own head. Okay, if I wanted to find the measure of angle F in that smaller triangle, F would be equal to 180 minus 171.146 minus 38 degrees. Okay, well, that means that F turns out to be a negative angle. Okay, F is a negative angle of negative 29 degrees, and that ain't cool. That's not fun. And so as such, what we notice then, or what we should say, is that there's only one triangle possible in part A. So my response is only one possible triangle in part A, and that's due to the fact that when I tried to solve for the measurements in that second triangle, I ended up getting a negative angle measurement. And so then I would recognize that there's only one possible triangle for part A, and that's the given triangle that we had to begin with here, EFD, the larger triangle with the dimensions that summed up to make 180 degrees. So today's lesson really focused on your ability to draw two triangles, which again is done by you placing this side length and this fixed side length here. So reorienting your triangle so the fixed side lengths are here, and we can swing that other side length of my side-side angle relationship to create a big triangle and a small triangle, to thus show that we can get differing lengths within my triangles. And so from that point, we're going to stop right now. We're going to pick it back up tomorrow, Thursday, to be able to get back in touch to reiterate some law of cosines practice and go over this ambiguous case of the law of sines one more time. If you have any questions, feel free to email me. Otherwise, I hope you have a great rest of your day, and we will see you on Thursday. Take care.